Okay, we're going to start talking about using a normal approximation for a binomial distribution. And if you may recall, there's your normal distribution. But have you ever seen a paranormal distribution? Haha, there's your joke. All right, so let's go ahead and take a look at binomial distributions. If you remember, those are where we have discrete probabilities or probabilities for discrete random variables. In this case, I have some Reese's Pieces. This is where you can go and play with the applet. And we're going to assume the probability of orange is 50% or zero point 0.5. The number of candies is 50, and we're going to take 100 samples. So if I were to draw samples, what would that look like? And so you can see here, I have 50, and I drew samples, and then I can also increase the number of candies and the number of samples. And you can see that basically it's bell-shaped and symmetric both times, and it looks like the normal model. Now, what gets interesting is when the p-value gets very low or very high. So if p is 0.1 and there are only 20 candies, what happens? Well, here we're drawing a sample, and you can see it's sort of skewed to the right, okay? And if we draw samples where p is very high at 0.95, so we'll change it there, it ends up being skewed to the left. So what we find out is if we use the rule n times p is greater than 5 and n times q is greater than 5, then we will have a distribution that's more symmetric, and we can use a normal approximation. Remember that q is 1 minus p. So let's go ahead and revisit a binomial distribution. We're going to be using this example in the entire set of notes. And the probability that someone tries to pad their insurance claims is 40%. You received 90 insurance claims. What is the probability that exactly half are padded? So we need to know P, which is 40% or zero point 0.4, and N is 90. And we're trying to find the probability that X is 45. We can use a binomial distribution with N and P and X, 90, 0.4, and 45. And we get a probability about 1.34%, which is this probability right here. Now, if I try to, now, first of all, recall when we use a normal distribution, we have an x left and lower and an x upper. So those go there. We put the mean for x as our third number, and our standard deviation for x as a fourth. Now, if you're saying, wait a second, what if I don't know the mean and the standard deviation? Remember that the mean is n times p, and the standard deviation is n times p times q. Q is 1 minus p when you take the square root of it. Okay, so we'll be using these values in this line for all of today's lesson. So now let's try using a normal approximation. So what could we do? Well, we know when we're doing normal CDF, we need mu and x. So let's calculate those first. N times p is going to be 36, and square root of NPQ is going to be this long number, 4.6475. If I'm going to do normal CDF, I could say, well, I want it to be 45. There's my mean, and there's my standard deviation. So what do I get when I put that in the calculator? I do second distribution to get to normal CDF. This is an older style calculator, so I have to separate my values with commas. And finally, after I get this long standard deviation in, what do I get for the probability? And this one gives me 0, all right? So I get 0. Now, sometimes on newer calculators, you'll actually get an error. So let's try 45 and 45. And believe it or not, on that one, unfortunately, there we go, 45 and 45, and the mean's 36, and the standard deviation is 4.6475. I'm also going to get 0. So what went wrong? Why didn't this work? Well, because we used a continuous distribution for a discrete variable. Remember that the normal CDF doesn't actually have specific values for discrete values of x. So how do we fix that? Okay, so we always need two x or z values for normal distributions because it's continuous. So I'm going to have my imaginary value here that I want. Well, to make it continuous and have some area, I'm going to have a left value on my box and an upper value on my box. The left value, I'm going to subtract 0.5 from it because for binomial distributions, we're going in integers. In this example below, I have 45, so the integer below would be 44. The one above would be 46. How far apart are they? They're 1, and I only want to go halfway. So if I subtract 0.5, that'll take me halfway down. Going halfway up, I would add 0.5. So on this example, remember that I still have the same mean and the standard deviation. I'm going to make a box around 45. The lower value is going to be at 44.5 because I'm going halfway to 44. The upper value is going to be 45.5 because I'm going halfway from 45 to 46. We can do normal CDF. Here's my x lower, my x upper, my mean, and my standard deviation, and there's my probability. By the way, this is very close to the 0.0134 that we got with Binomial PDF. Now let's look at the case where we want probability that x is greater than or equal to a number. So first of all, let's put our number x. If we want it greater than or equal to this number, then we want to shade to the right. Now the question is, what is a left or lower boundary for the area I'm looking at? Because I want to include the number x is greater than or equal to, I'm actually going to want to be on this left side of my red box. And the left side I can figure out by subtracting 0.5 from x. The upper I want to keep going to the right as far as I can to infinity, but that takes too long to plug into the calculator, so I'm going to use 1,000. Now remember, keep track of your x's. If they're close to 1,000, you're going to have to use a number that's a lot bigger. Okay, so let's re-examine the problem, and this time instead of doing exactly half, we're going to find the probability of half or more. So first of all, I'm going to want, there's my half and there's more. Do include the red bar because it's 45 or more, so we're going to include this 45. Now, the right side's pretty easy to figure out. That's infinity or 1,000 because of more. The left side's going to be 44.5 because I want to make sure if I was at 45.5 and went to the right, I would miss the half value. And it does say half or more. So basically, I'm doing normal CDF of 44.5 to 1,000 with a mean of 36 and a standard deviation of 4.6475. which gives me 0.0337 or 3.37%. Now let's look at the case where we want the probability that x is greater than a number. Not greater than or equal to, but greater than. Well, we still have our red box here on x, wherever that is. And since we're doing greater than, I'm definitely shading to the right. Now, do I want to be on the left side or the right side of this box? Well, if my number is in here and I want to be greater than, I need to be on the right side of the box. So to calculate what the lower value is for my normal CDF, I'm going to add 0.5 to x. And then the upper is way over here somewhere, it's infinity, or 1,000 if that is high enough on your problem. And basically you do normal CDF. Now, let's go ahead and look at this variation of the problem. So if I said, what is the probability that more than half are padded? How does that change? Well, first of all, we're going to be to the right here of 45, and we're not going to include the red bar because we want more than 45. So first of all, the lower is going to be 45.5, and the upper will be 1,000. So we do normal CDF of 45.5 to 1,000. And we get 0.0205. What if we want the probability of x is less than or equal to a number? So I'll have x here. Since we're on the less-than side, we're going to shade. But what do I want for my lower? Well, that should be kind of easy. That should be negative infinity or negative 1,000 if that's far enough away. But what's my upper? Well, if I'm less than or equal to, I want to include the red bar. And so I'm going to be on the right side. That's going to be my upper, and I'll want to add 0.5 to whatever my original x is. So in this example, less than or equal to is like the words half or less. So I'm going to want to include 45 in everything below. So we are going to include the red bar. So the lower value for our x is negative 1,000 because of less. The upper is going to be 45.5 because I want to include this. And then I'll do normal CDF of negative 1,000 or 45.5. And I get 0.9795. By the way, if I subtract that from 1, the complement is 0.0205, which is what we got when we said what's the probability of more than half. And that makes sense. Finally, we're going to look at the probability that x is less than a number. So if x is less than a number, first of all, we're shading on the left of our box. And where do we want our lower to be? We don't want to include the number, so we want to be on the left side. All right, so our x lower, first of all, is negative 1,000 or negative infinity. And our upper up here is going to be on the left side of the box because we don't want to include the actual value. We want to be less than that value. So we're going to subtract 0.5 from x. An example of that problem is if I ask, what is the probability that less than half are padded? Well, less than half means I don't want to include 45, all right? So first of all, x lower is negative 1,000 because we're going all the way to the left, and that's pretty far away. X upper is 44.5 because we don't include 45. So we'll just do normal CDF of negative 1,000, 44.5, and there's our mean and our standard deviation, and we get 0.966.